Hey everybody, we're live and in stereo. So this is the day you all have been waiting for, AS level organic chemistry. Now, fun fact, this particular part of chemistry is actually the easiest out of all of the chemistry that you've studied up until now. Students, they dread organic chemistry. It's my favorite. It should be your favorite. It should be every chemist's favorite aspect, because organic chemistry is filled with discoveries and it's filled with inventions and it's filled with so many practical applications that if I start talking about the practical applications of organic chemistry, you will see it all around you. Every single substance will around you will include some aspect of organic chemistry, be it a lot of organic chem or a tinge of organic chem, but you'll always be seeing organic chem all around you, right? Now this is in fact the easiest part of chemistry, only and only if it is conceptually taught to students in a very story-like manner, in a very coherent manner, and that is what we'll be doing. I am a master of organic chemistry, self-proclaimed master, but yes, no doubt I am, and inshallah you will see how we go through organic chemistry one by one. We'll be starting off with the basics of organic chemistry, and then we'll be moving on to more and more complicated things, right? And the way I want to teach organic chemistry is to first of all work on your basics, teach you guys how to name compounds, teach you guys how to draw compounds, and be it, compounds like alkanes, alkenes, alcohols, carboxylic acids, ketones, and aldehydes, all of that good stuff we'll be learning slowly and gradually. Initially we'll just be covering the surface of all of these families initially, so that we learn how to name them and we learn how to draw them, and we're going to first and foremost cover these aspects along with the aspects of isomerism. And so after that we'll officially be starting off with every single chapter on its own. We'll be officially studying every single family in itself, right? So as you said, can we still register for your class? Yes, this class is for the registered students, but if you're from the outside, it's fine. We'll change the link as per Raima's request, but you can absolutely register for my classes till the 1st of January. I've extended the deadline till the 1st of January. You can register. After the 1st of January, if you want to register, the price of my portal will be doubled. So this is what we've decided. It will help more poor people along the way. So that's what's decided. Chalo, without further ado, let's just start off with organic chemistry. I'll start off with a beautiful story of how organic chemistry was actually discovered by humans, and then we're going to slowly and gradually learn things from O level, recap certain things from O levels, and also learn a little about AS level. ठीक है? Chalo, let's start. So I'll write down the topic, organic chem. Buckle up everybody, you'll enjoy this ride. I promise you'll enjoy it, right? Now, what exactly is organic chemistry? Let's first talk about the initial idea. Basically, what scientists used to think was that organic chemistry was the chemistry that only existed in living things. That's what scientists used to think, right? That it's the living things chemistry. And scientists initially thought that this particular part of chemistry cannot be recreated in labs. Right? So it can't be recreated in labs. It's the chemistry of living things. It exists in living things and all of that stuff, but it can't be made in the lab. And the reason for this idea was pretty basic. The reason for this idea was that living things chemistry was very complicated, and you'll see a lot of complicated structures along the way. So it was a very complicated idea, and scientists never thought that they'd be able to make it in labs. Hence they called it organic chem. Organic basically means what? Living chemistry, right? So it was the chemistry of living things, right? And it was very complicated, unlike inorganic chemistry, in which you could easily make things like NaCl, which is literally no, it's just edible salt, right? So you could make things like NaCl, you could make things like table salt, your calcium hydroxide, which could treat acidic soils, you could make acids, you could make bases, and all of that good stuff. The juices, the masala, certain juices, certain masalas. Nowadays you also have organic organic stuff, but you were able to make all of these things, right? And that's why the name organic came into being, which is basically what? It's the chemistry of the living. How beautiful. And inorganic chemistry was, all the other parts of chemistry were classified as inorganic chemistry because you could actually make everything in laboratory. It wasn't that complicated, but nobody could have fathomed the idea of making these very complicated molecules inside labs, inside these laboratories, right? And the second notion about organic chemistry was that scientists also added that it's the study of carbons. Scientists also added along the way that it's the study of carbon containing compounds, right? And the reason why they called it, the study of carbon containing compounds, or also as carbon chemistry, is because whenever they used to see these very complicated living thing chemistry, they used to look at those molecules and it used to be filled with carbons. And so that's why, they said that organic chemistry is the study of living things. There are very complicated molecules. It can be recreated in labs, but it's also the study of carbon containing compounds, because in fact all of these very complicated compounds did contain carbon atoms, right? But both these notions, number one, which is that organic chemistry is the chemistry of living and things, and that it's all comprised of carbons and carbons, both of these notions were one fine day, they were demystified, and scientists actually understood the real idea of organic chemistry. Something really, really magical happened one fine day to demystify these two concepts. And what actually happened, sir, in 1828, if I'm not wrong, you guys can check out the proper date, but as far as I remember, it was a fine day in 1828 where a scientist named Frederick Wöhler was playing around with certain chemicals, right? And he wanted to make an inorganic compound, because remember, up until 1828 people thought that organic chemistry cannot be recreated in labs. It contains carbons, very complicated molecules, very complicated compounds. It's the study of living and it can't be recreated, blah blah blah. But in 1828, this guy whose name is Frederick Wöhler, he actually started to make an inorganic compound, because he never thought that organic compounds can be made. And that inorganic compound was called ammonium cyanate. You know how it looks? Just for your idea, this is basically ammonium cyanate. It has ammonium ion and it has the cyanate ion. If I'm not wrong, cyanate ion is NCO minus, right? And ammonium ion is NH4 plus. So he was playing around with these certain molecules in order to make this inorganic molecule called ammonium cyanate, right? And that's what he was doing. And you know what actually happened? He mistakenly heated this. He mistakenly, when he was making ammonium cyanate, he heated the entire mixture, and what he ended up with was something really, really magical. He ended up with something called urea. And you know what urea is? Urea is an organic compound, or an organic molecule compound, potato, right? And this is how urea looks like, by the way. Nobody cares, but this is how urea look like. It's in your piss as well, in pishy, right? At times. So that's the idea, and this is when scientists realized that, okay, organic chemistry is not just it's not just limited to living things. It can also be synthesized. It can also be recreated. And thereafter, consequently, scientists started to work towards this. And now you can see organic chemistry in your clothes. Nylon 66. Your moms, when they go to shops, they buy clothes made from nylon at times. And there's this idea about nylon, that nylon was discovered when a scientist from New York was traveling on an interconnecting flight, and a scientist from London was traveling, and they both were working on the same idea. I don't know how much truth there is to this story, but a lot of teachers, they tend to tell this story that nylon is called nylon because it's New York and London. And 66 is because of its monomers. You'll learn that later on. But that's the idea, that nylon was synthesized. Then you had terylene, which was synthesized. You've already studied a couple of them in O-level IGCSE. So we started to later on synthesize organic compounds. But because the name was so beautiful, organic chemistry, they really did not want to change it. They never really changed it. It is still to this date called organic chemistry, the study of living thing chemistry, although you now know that it can be synthesized in labs, right? And the second notion, that is the study of carbon containing compounds, that is true to much extent, because a lot of these organic molecules, they will all contain carbon atoms. That's true. But the problem with this was that it not just contained carbon atoms, it also contained hydrogen atoms, it also sometimes contained nitrogen atoms, it also sometimes contained oxygen atoms, sulfur atoms. All these atoms, traces of sulfur, oxygen, nitrogen, hydrogen, they are all a part of organic chemistry. So it's not just limited to carbons. There's also hydrogens involved, some nitrogen, traces of sulfur, even oxygens involved. All of these atoms together involved in a lot of these organic compounds, right? And then when science started to progress more and more, we realized that, okay, this is now the basic idea of organic chemistry. But a student like Hamza got up and Hamza said, Sir Suleiman, stop playing around with us. I said, why, Hamza? What's wrong? He said, okay, sir, you are saying that it will contain carbon compounds, but organic chemistry is filled with carbon containing compounds. There will be carbon atoms in every single area of organic chemistry, and that's true. But why don't you study carbon dioxide in organic chemistry? Why don't you study carbon monoxide as a family of organic chemistry? Why don't you study sodium hydrogen carbonate in organic chemistry? Sir, they also contain carbon. So Hamza started to fight with me, said that if you're saying that all carbon containing chemistry will be organic chemistry, why aren't these classified as families of organic chemistry? And that was a very valid point that Hamza raised. And I said, Hamza, wait a moment, please understand that although organic chemistry will have a lot of carbon atoms, not all carbons that you'll see will be a part of organic chemistry. Like carbon dioxide is carbon in carbon dioxide, CO2. This is not going to be studied as a family in organic chemistry. This is inorganic chemistry, not organic chemistry. This is a part of inorganic chemistry. It's not organic chemistry. It's not studied as a family when you study organic chemistry. This is basically baking soda. This is not studied as a family when you're studying organic chemistry. So Hamza said, sir, how come? Which families do we actually study? I said, Hamza, as a food of thought, you study, as an initial learner of organic chemistry, you study families like alkanes, you study families like alkenes, you study families like alcohols, you study carboxylic acids, families like carboxylic acids family, you study esters, you study aldehydes in A levels. This is something new. You study ketones. You study, a lot of other families as well. You studied polymers and so on and so forth. Throughout your life and your chemistry career, you will come up with a lot of families. And all these families have one thing in common. They all have carbons. But then Hamza said, okay, sir, if they all have carbons, then why don't we study these as a family? Because, Hamza, there's the idea that although they all contain carbons, their carbon is a little special. Hamza said, sir, how is their carbon a little special? Hamza, their carbon is a little special because in all of these families that we study, their carbons has a certain ability that is not found right here or here or here. And what is that ability? It's the ability of catenation. In all of these families, carbon has undergone something known as catenation. Carbon has this very special ability that it has reflected in all of these families, which is that it has undergone something known as catenation. Now, what exactly is catenation? Catenation is the ability of carbon to make long chains or rings. So what really happened in all of these families and a lot of other families that you'll study throughout your life is that carbon in all of these families has undergone the ability of catenation, which is all of these carbons have the ability to make long chains, rings, which is not present here. And that is the reason why you don't study them as a family in organic chemistry. It's not actually a family. These are the families of organic chemistry, and much more you'll learn throughout your career as an organic chemist. So catenation is this very special ability of carbon which is reflected here, which is the ability of carbon to make long chains or rings. Now, the rings bit, you're gonna study this in A2 chemistry. Rings is a part of A2 chemistry. You'll study benzene, phenol, and all of that good stuff. That's a part of A2 chemistry. But in AS level chemistry, we are just going to stick to these long chains that carbon can actually make in all of these families. And you've seen these long chains in O levels. Remember, chains like this, these molecules and more molecules. You had more molecules that looked something like this. They were all simple molecules, but they in this particular family, carbon had the ability to undergo to make these long chains or rings, which we call catenation. And when does carbon make these long chains or rings? When does carbon make these long chains or rings? When it has undergone catenation. And carbon can make these long chains or rings with other carbon atoms, right, in that particular family. And so this is why these families were given birth to, and more and more and more and more. So in organic chemistry, we'll not just focus on this ability, rather we'll focus on how this ability results in the formation of different millions and millions and billions of molecules, which we also call organic synthesis. You will study that as well later on as you move on with your AS level course, and you learn how their structures are linked, how their names are made, and all of this idea will be studied. So in summary, organic chemistry is not just limited to living things. We can make them in laboratories, and it's not just the mere presence of carbon atoms, it is also the ability of carbon atoms to make long chains or rings. And rings part, we know we are going to study this in A2 chemistry, right? Now let's start off with the basic idea of organic chemistry families. We're going to start off with alkanes, okay? And today you're going to learn AS level stuff. So I'll recap certain O level stuff, and we'll also learn AS level stuff, okay? Okay, so let's start off with the basic family. Now understand that I'm not going to go into the depth of every single family as of now. I'm just going to teach you how to name these families, and how to name compounds in these families, molecules in these families, and how to draw them. What is a displayed formula, a molecular formula, general formula, skeletal formula, structural formula. I'll teach you all of that for every single family. Then we're going to learn isomerism, and then we're going to slowly and gradually start off once again with every single family, and then that time we'll go into the very depths of every single family. Okay? So let's start. Let's start off with alkanes, sir. Now, what exactly are alkanes? Have you ever seen alkanes? I always start the O-level classes like this. Have you ever seen alkanes? Yes, we have, because you studied O-levels from me. You guys have seen alkanes. Alkanes is where it's literally the natural gas. It's a part of the natural gas that comes in your home, and you use it for cooking. It's the cooking gas, you know, which is piped inside your homes as fuels for your scrumptious food. You know, and the largest constituent of this natural gas is actually an alkane. That's basically methane, right? Then you have cylinder gas. You know, if you guys go on and get some pakoras and samosas from outside your school in these winters, you will enjoy it, and you'll see this cylinder gas that the vendor is using to make those samosas and pakoras for you all, or these garam parathes for all of you. That cylinder gas is basically a mixture of different alkanes. You have LPG gas, liquefied petroleum gas, that's also alkanes. You have blow lamps, which are basically devices which produce hot flames, and that is used to heat metal or remove old paint. Those blow lamps are basically what? They are alkanes. And it's all around us, guys. The white spirit that you guys use, that's basically alkanes. You know, the white spirit that we use, that's basically alkanes, you know, to obviously remove paints and stuff like that. The gasoline that you add to your cars, petrol, or the gasoline that we add. If you're in America, you call it gasoline. If you're in the UK, you call it petrol, or in Pakistan, because we are slaves of the UK, so we call it petrol. The fuel that we use in our cars, that's basically an alkane, right? It's actually C8H18, by the way, and you learn this, what it's called later on. If you don't remember O levels, don't worry, we're recapping everything, right? And so that's the idea. It's fuels as well. You have waxes. You know, back in the day when you did not have these batteries, we used to use these wax candles. And so the wax candle, the lubricating, the part of the wax candle, the part of the wax part of that candle was made from an alkane, right? It is used in lubricating oils. So it's all around us, guys. Alkanes are all around us. But the question is, sir, what exactly is an alkane? You're giving us practical examples. Stop trying to be smart with us. What exactly is an alkane? Sir, You are very right. I was just giving you guys practical examples of alkanes. But what exactly is an alkane? Let's first of all look into that. As chemists, we need to understand the chemistry. Okay, what constitutes an alkane? Sir, alkanes are saturated hydrocarbons. Now the question that you guys should ask is what? What question should you guys ask? Sir, what is meant by saturated? I don't know. I've forgotten O levels. What is meant by hydrocarbons? Sir, I don't know. I've forgotten O levels. Let me tell you. Saturated means that they are basically saturated compounds are those compounds in which you have carbon-carbon. They are compounds in which you have carbon-carbon single bonds only. Right? So whenever carbon makes a bond with another carbon, it must only be a single bond. For example, these are a lot of carbon atoms. It's just gonna be single bonds. The moment it's a double bond or a triple bond, you will not call it saturated. My question, sir, which of these compounds is saturated? Sir, which of these compounds is saturated? The first one, the second one, and the third one. Which of these compounds can I call saturated? So we all know that the first compound is saturated. Why is this saturated? Because it has carbon-carbon single bonds only, nothing else. But the second one, it's not saturated because there's a carbon-carbon double bond. The third one, it's not saturated because there's a carbon-carbon triple bond. So saturated compounds are those compounds in which you have carbon-carbon single bond. Sir, why can carbon make a double bond and triple bond? Because we know from our chemistry, this is a prerequisite of organic chemistry, that the only thing you should know is that carbon makes 4 bonds in total. This is what you guys should remember. It's in group 4. It needs 4 electrons to become stable, and that's the reason why it makes 4 bonds in total. So it can make single bonds with other carbon atoms and all the other bonds with other atoms. It can also make a double bond with other carbon atoms and other single bonds or double bonds with other atoms, and it can also make triple bonds. I'm not showing all the atoms. There are other atoms present as well, obviously, but I'm just focusing on these carbons. My question to you guys is, and this is a common mistake amongst all O-level IGCSE students, is this a saturated molecule? Is this a saturated molecule? I'm not showing all the other atoms. There are other atoms bonded to these carbons. I don't want to look into it. But is number 4 a saturated molecule or a saturated compound? Now, those who've studied O levels from me, they're all correct. Some of you guys who haven't studied O levels, you are also right. But some are also wrong. So a lot of students are saying yes, and some are also saying no. The ones who are saying no, you guys are all incorrect. Please remember, saturated only has to do with the single bonds between carbons. There can be double bonds that carbon is making with other atoms. We couldn't care less about it, right? All of these carbons have single bonds with each other. Therefore, I can call this as a saturated molecule. If you don't know that, if you did not know that, now you know it, right? So saturated molecules or saturated compounds are those compounds in organic chemistry, are those compounds in which you have carbon-carbon single bonds only. We couldn't care less about the double bonds that it's making with other atoms, but it shouldn't make a double bond with carbons, right? So yes, saturated means carbon-carbon single bonds only. So whenever carbon bonds with another atom, it's gonna make carbon-carbon single bond. Done. Now, what is meant by hydrocarbon? Hydro literally is derived from the word hydrogen. Carbon is derived from the word carbon. It's a pretty basic concept. So hydro means it must have hydrogen, and carbon means it must have carbon. And so hydrocarbon means those compounds in which you have hydrogen and carbon atoms only. So you only have hydrogen and carbon atoms, nothing else. Only hydrogen and carbon atoms, right? So the first idea for an alkene is, and both these conditions must be there. Both these conditions must be there, right? It can't be, you can't say, hey, it's an alkene because it's saturated, but it's not a hydrocarbon. No. Or it's a hydrocarbon, but it's not saturated. No. It must, both these conditions must be met for a compound to constitute as an alkene. If you want to call something as an alkene, it must be saturated, which means that all the bonds between carbon-carbon atoms must be single bonds, and it must be a hydrocarbon, which means that after these single bonds, you must have hydrogen atoms only, right? So it must only contain carbon and hydrogen atoms. Yes, that's it. So for example, I say you have an alkane with of 2 carbons. You have a 2-carbon alkane. Sir, how do you draw a 2-carbon alkene? Pretty simple. If it's 2 carbons, I'm going to draw 2 carbons. Done. It's an alkane. So alkanes, you go into the very basic definition of an alkane. What is an alkane? Alkane is a saturated hydrocarbon. Saturated means what? compounds containing carbon-carbon single bonds only. Remember, only is the key word. You have to write only in the exam. So carbon-carbon single bonds only. So can I make a single bond between carbon and carbon? Absolutely, I have. Now, the next part of drawing an alkane is that it must be a hydrocarbon, which means it must contain carbon atoms and hydrogen atoms only. So you've already drawn the carbon atoms. What other bonds will this carbon make? How many other bonds will this carbon make, and with which atoms would it make these bonds? How many bonds would this carbon make, and with which atoms would it make those bonds in order to be a hydrocarbon? So you've already drawn carbons. What should be the other element that carbon will make the bond with? It must be hydrogen, right? Because carbon is met, you just need hydrogens. And how many bonds would the leftmost carbon make? In total, it would make 4 bonds. I know that the leftmost carbon in totality is going to make 4 bonds. It has already made 1 bond here. So how many more bonds would it make? 3 more. 1, 2, 3. And so these 3 bonds are hydrogens, right? Similarly here, it's 1 carbon right here. It has made 1 bond already. It'll make 3 more bonds, because in total carbon must make 4 bonds. So it'll make 3 more bonds. And what would these 3 bonds be with if it were to be an alkane? Well, if it were to be an alkane, these 3 bonds that carbon is going to make is going to be with hydrogen. And especially if it's a 2 carbon alkane, right? Some students tend to ask me, sir, what if this carbon makes another bond with hydrogen, a carbon, single bond with carbon? It can do that, but then it's not a 2 carbon alkane, then it'll be a 3 carbon alkane. We just talk about a 2 carbon alkane. Done? So that's the idea. That's the idea. Now the question is, sir, how do you name these alkanes? I'll tell you. I call this particular alkane as ethane. The question is, sir, how do you know it's ethane? How do you know that this alkane is known as ethane? I'll tell you. It's pretty basic, pretty simple. Sir, in order to know that this particular compound is known as ethane, you need to know something known as a nomenclature. Nomenclature. Nomenclature is just a naming system. It's just a fancy way of saying naming system. Chaudhary, that's a very good question that every student asks me. Please wait until we finish off this. Ke 1 carbon molecule ka kya hota hai? Just wait, right? Just wait a moment. You'll understand 1 carbon ka just in a while. Okay. This is a common question amongst O-level IGCSE students as well as AS students. I'll answer it later on. Okay. So what is the naming system? I'll show you. This is basically the nomenclature or the naming system. This fella right here. Meth in Greek means 1. Eth means 2, prop means 3, but means 4, pent means 5, and so on and so forth. Hex means 6, hept means 7, oct means 8. These are all called prefixes. In English, whenever you make a word, whenever you form a word, normally there's going to be a prefix, the part which comes before, and I'm going to be a cool Gen Z guy, so I'm going to write before like B4, right? And there's always going to be a suffix. A suffix is the part that's going to come after, right? So whenever you make a word, it must contain, at times, usually it contains a prefix and it contains a suffix. And when we study organic chemistry, all the molecules have a certain prefix and they also have a certain suffix. We actually call them stems. In chemistry language, we call these prefixes as stems, right? And what these stems do is that these stems tell us the number of carbons. These stems, they tell us the number of carbons, sir. Now, sir, if you ask me, sir, why do they tell us the number of carbons? These are just Greek prefixes used to denote numbers, like number of carbons. For example, if I say, what's a shape with 5 sides called? Can anybody who's studied anybody who studied O-levels and IGCSE, can you guys tell me a shape with 5 sides? What is it called? What is a shape with 5 sides called? And what is a shape with 6 sides called? Sir, a shape with 5 sides is called pentagon. Which is also present in the US. And a shape with 6 sides is called hexagon. You all have studied O-level IGCSE. Please, I hope you all know this. What is a 7-sided shape called? I hope you all know this from O-level IGCSE math. 7-sided shape, it's called a heptagon. 8-sided shape is called an octagon. 9-sided shape is called a nonagon. I don't know if you've been taught this, but we used to be taught this in elementary classes. 10-sided shape is called a decagon, if you guys know. Now, see, it's very simple to call these shapes the way I'm calling them, because literally pent is a prefix. Pent literally means 5. Right here it's written 5 prefix. 5. right? It represents the number 5. Yes, in organic chemistry, it'll represent the number 5, and this 5 will tell us the number of carbons, but anywhere else, it just means 5. And agon is the Greek suffix, which means sides. So when I say pentagon is called pentagon, there's a reason behind it, because pent means 5 and agon means side. So it's a shape with 5 sides. Hex means 6, agon means side. So a shape with 6 sides, and so on and so forth, right? Why is octopus called octopus? What's the spelling of octopus? I don't know. Whatever it is. But why is it called an octopus? Because oct literally means 8. It has 8 tentacles. And apus literally means what? Tentacles. Maybe. I'm just making this up. I don't know if it means tentacles or not. But octopus is called an octopus because it has 8 tentacles. Right? Yashai Singh present. Yes, Pentagon is, the military place in the US. Yeah. Similarly, if I say, hey, a decade has passed by. When I say a decade has passed by, what does that mean? Decade means 10 years. How does Sir Suleiman know that decade means 10 years? Dec literally stands for 10. Right here. So there's nothing, rocket sciencey about these prefixes. These are Greek prefixes, and we've used it in our mathematics. We've used it in every single place. Dec means 10. Aid would probably mean years. So decade is basically representing 10 years. Centipede. Why do you call it centipede? Because centi means 100. A pede maybe means the tentacles. 100 tentacles, insect. Whatever. So we've seen these prefixes in our day-to-day lives in a lot of detail, right? And so when we talk about naming organic compounds, these prefixes are basically our friend, right? So if you don't know these prefixes by heart, you're gonna get cooked. So you should remember them from O-level and IGCSE. Bute means it's spelled but it's bute. It's pronounced bute. So bute means 4, probe means 3, eth means 2, meth means 1, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and 10 is dec, right? Now, if I say I have an alkene which has about like 2 carbons. There are 2 carbons to that alkene. There are 2 carbons in that alkene, and then there's another alkene which has 3 carbons. And then there's another alkene which has 4 carbons. And then there's another alkene which has 5 carbons. And then there's another alkene which has 6 carbons. Can you guys name these alkenes? And can you guys draw these alkenes? And then there's another alkene with 7 carbons. Chalo, let's start off with it. This is all O-level recap, but we're going to start to slowly and gradually move into AS level. So just bear with me. I know some of you guys might be bored because you might think this is all O-level, so what's new about it? We'll slowly transition into it, right? So I talk about an alkane with 2 carbons. Basically, the way you write the name is you use the prefix and you use the suffix. The prefix is what? 2 carbons means what? If you go to your nomenclature, you see 2 stands for eth. So I'm going to replace 2 with eth, because 2, wherever you see 2 in organic chemistry, that means eth, right? We represent it with the prefix eth, which is our stem. We call this our stem. It tells us the number of carbons. So eth means the number of carbons, eth, right? Now, and because I'm saying it's an alkane, eth would be the prefix, and because it's an alkane, the A and E would drop down to tell every single scientist that it's a 2-carbon alkene. If I were to name a 3-carbon alkane, what would it be called? 3 carbons means what? 3 means in organic chemistry, 3 means what? Prop. So prop would come here, and then the A and E would drop down right here, because it's an alkene. So if it's an alkane, the alk bit, remember, the alk bit is replaced with the prefix, and the A and E is just the suffix. It drops down to tell me the family. So if I look at the name actually tells you 2 key features. It tells me the number of carbons. This is what the name tells you. It tells you the number of carbons. Probe means 3, so this must have 3 carbons. And A and E literally tells you the family. So the name is very crucial. It tells you the number of carbons as well as the family. How easy, how beautiful. It's like a puzzle. It's like a puzzle. Absolutely, you all are right. 4 carbons. 4 means what? Bute. And if I were to say it's a 4-carbon alkane, I must end it with the suffix of an alkane. The alk bit is replaced with bute. See, the alk bit right here. The alk bit is replaced with but, and the A and E drops down. But tells me there are 4 carbons. A and E tells me the family is alkanes. Similarly, 5 carbons. Come on, you guys can do it. Pent stands for 5, and the A and E drops down. Pentane. 6 carbons. Hex means 6, and the A and E drops down to tell me it's an alkene. 7 carbons. 7 means what? Hept. and the ane drops down to tell me it's an alkane. So how do you name alkanes? You use your nomenclature. You just see how many carbon alkane am I talking about? I am talking about a 3 carbon alkane. So 3 means what? Prop, and it's an alkane. The ane must drop down. So propane. The suffix is ane and the prefix is prop. Right? The suffix tells you the family, the prefix tells you the number of carbons. How easy, right? So if I start off with these alkanes, ethane is an alkane. And what does it tell me? It tells me that eth means 2 carbons and ane means it's an alkane. So it's a 2 carbon alkane. And then similarly, you have propane. Then propane is what? Prop means 3 carbons and ane means it's an alkane. So 3 carbon alkane. And then butane is a 4 carbon alkane, and so on and so forth, right? Pentane is a 5 carbon, hexane 6 carbon alkane, heptane 7 carbon alkane, octane, nonane, decane, undecane, and that's not a part of your course. Let's not go down that lane, right? Undecane and so dodecane and whatever. Nobody cares. Right? Now, the question is said we've learned the naming now. The naming is pretty simple. We just need to know our nomenclature. We just need to know how many carbons do we need to name. And once you know this table, you would say, hey, if you want to name a 4 carbon alkane, it must start with but and it's an alkane. ane would come at the end, butane. If I were to name a 9 carbon alkane, non would be the 9, represent 9, and ane would mean it's an alkane. So nonane, decane, dec, and ane would drop down. Please, if you make a spelling error in organic chemistry, you're not getting a dime mark for it. Okay? So we've learned the naming for alkanes, and we have also studied this in O levels, but I'm just recapping it. Done. Now, the next question that you asked me, sir, how do we draw them? We've learned how to name them, but how do we draw them? That's the second question that students should ask me. It's pretty simple. Sir, the drawing has to do with naming. If you can name it properly, you can absolutely draw it. Sir, how would you draw it? Eth means how many carbons? Sir, 2 carbons. Okay. Prop means how many carbons? 3 carbons. 1, 2, 3. And but means how many carbons? 4 carbons. How many carbons? 4 carbons. Let's draw them. 1, 2, 3, 4. Done. So we've drawn the carbons. That's it. That's the first part done. Done and dusted. See, if you start to look at it like a puzzle, eth means carbons. A and E would mean the family, right? So eth means carbons. I've drawn carbons. So it won't have more carbons than this, right? Eth means 2 carbons. It can't have more than 2 carbons. Prop means 3 carbons. Can't have more than 3 carbons. But 4 carbons. Can't have more than 4 carbons. Now, we've drawn the carbons. The next part is look at the family. The family is A and E. It's a family of what? It's a family of alkane. And now, you lot tell me that alkanes are what? They are saturated hydrocarbons. You know that. And saturated means what? That carbon and carbon must have a single bond with each other. Whenever there are carbons being bonded to other carbons, they must have a single bond. So let's draw those single bonds. Tuck, 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 and tuck, and tuck. Done. That's how easy it is. One part of the drawing done. The next part is it's a hydrocarbon, which means it's a compound which contains hydrogens and carbon atom only. It contains hydrogens and carbons only. And similarly, saturated means carbon-carbon single bonds only. Hydrocarbon means hydrogen and carbon only, nothing else. Now we've already drawn out the carbon. We are restricted by the name. The names tell me eth. Eth means 2 carbons. I can't draw more than 2 carbons. Can't draw more than 3. Can't draw more than 4. So we're already done with the carbon bit. Now we just have to add on the hydrogens, right? And how do we add on the hydrogens? So we check out the carbons. I know that this carbon can make a total of 4 bond. Every single carbon can make a total of 4 bond. It has already made 1 bond right here. So how many more bonds would it make? It can make uno, dos, tres. It can make 3 more bonds. And these 3 bonds are definitely, most definitely with hydrogens, right? Similarly here, 1, 2, 3. Now I'm not going to write H, H, H all the time, but just straight sticks would mean hydrogen, right? Similarly here, this carbon has made a single bond. How many more bonds would it make? It would make 3 more bonds. Why? Because a carbon in totality can make 4 bonds, and these 3 bonds are going to be with hydrogens. So these are hydrogen, hydrogen, hydrogen. The middle carbon has made 2 bonds. How many more bonds would it make? It can make a total of 4 bonds. So how many more? 2 more. Hydrogen and hydrogen. This carbon has made 1 bond. How many more bonds would it make? Uno, dos, tres. That's it. Because it has to complete the total number of 4. Right? Similarly here, now you can quickly draw this. 1 carbon, it has made a single bond here. How many more bonds would it make? 3 more. Tuck, tuck, tuck. This carbon has made 2 bonds. 1 here and 1 here. It can make 2 more. with hydrogens, 2 more with hydrogens, and this would make 3 right here. Your guys' job is to draw pentane. Be quick. Draw pentane. Shabash. Draw it the same way I draw it. Don't do apni terneli. Don't do it directly. Draw it with the same logic I've taught you. Split it, because this logic will help you guys when you learn these very complicated molecules, 2-methyl, 4-ethyl, and blah 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 blah. You will be very, very easy. You'll be an expert at drawing this if you learn the concept behind it. Fatma, I'll jump off a roof and kill myself. Matlab, please, whatever I'm teaching right now, please just let's study that. After this, whenever I feel the time to teach you guys reactions, I'll teach you everything. I've not stepped down from teaching you guys a particular concept. I've taught more than what is required for your syllabus all the time. Take it. So when I teach reactions, I don't know when I'll be able to teach them. Once I'm done with all of this, you'll learn when the reaction starts. ठीक है. So please, जो करा रहा हूँ वो कर लें पहले. ठीक है. Moving on. Sorry for the tantrum, guys. So pent means how many carbons? 1, 2, 3, 4, 5. 5 carbons. A and E means what? It's an alkane. Alkanes are what? Saturated hydrocarbons. Saturated means carbon-carbon single bonds, tuck only, right? And hydrocarbon means all the other bonds, they are carbon and hydrogen atoms only. So carbons are already drawn, all the other bonds must be with hydrogens, and this is the structure. And by the way, this particular representation is called displayed formula. Now, what exactly is meant by displayed formula? Displayed formula. What is a displayed formula? It's also called a full structural formula. It's called a displayed formula or a full structural formula even. And what exactly is this? In Bato mein, we've also learned how to draw the displayed formula or how to draw the full structural formula. It basically shows you all the bonds. It shows us displayed formula is the type of formula in which you show all the bonds, all bonds between all atoms. And you'll see we've shown all atoms and all the bonds between atoms. You have to write H's here. I have not written H's, but in the exam, if you just draw this, you'll not get any mark. You have to write H everywhere. I'm just short on time. Awesome, Junaid has drawn it with sticks. So displayed formula is the type of representation in which you show all bonds between all atoms. These are all the atoms which I've shown, and I've shown all the bonds with all the atoms. That's the first type of representation. The second type of representation is called the molecular formula. Now, how do you write the molecular formula? In the molecular formula, what we actually do is we look at the displayed formula and we say, okay, this is the displayed formula. We're gonna write the elements. Which 2 elements do I have? I have carbon and hydrogen. So these are the 2 elements. I'm gonna write the 2 elements, done. And then I'm gonna write the number as their subscript. Subscript means the one that comes at the one. One is superscript, like x to the power of 2. This 2 is called superscript. X to the base 2, that's called subscript. So we write the number of a particular element as the subscript in a molecular formula. So if you have 2 carbons, you have 2 elements, carbon and hydrogen. And how many atoms of carbon do you have? 2. I'm just going to add a 2 here. How many atoms of hydrogen do you have? 1, 2, 3, 4, 5, 6. I'm just going to add a 6 right here. So C2H6 is the molecular formula. Similarly here, 3 carbons. I'm going to first write the elements, carbon and hydrogen. How many carbons do you have? 3 carbons. Write it as the subscript. How many hydrogens do you have? Count it out. 1, 2, 3, 4, 5, 6, 7, 8. Write it as the subscript. C3H8. Then again, here, if you count the carbons, C4, how many hydrogens do you have? 10. Count it out. Similarly, here you have 5 carbons. 1, 2, 3, 4, 5. And how many hydrogens? If you count it out, there will be 12 hydrogens. Right? So this type of representation is called the molecular formula, in which what we do is we show the number and type of different atoms in a molecule. Hence called the molecular formula. We show the number, which is 2 carbons and 6 hydrogen, and the type. Number and type. And number is not NO number, NUMBER number. I'm just writing it as a shortcut. So it shows me the number and type of different atoms in a molecule. Which different atoms you have? You have 1 atom of carbon and the other atom of hydrogen. These are the 2 different atoms. And what's the number? It's 2 and 6. Which two different atoms do you have? Carbon and hydrogen. What's the number? 3 and 8. Which two atoms do you have? Carbon and hydrogen, different atoms. What's the number? Carbon is 4, hydrogen is 10. Which two different atoms do you have? 5 carbons, carbon and hydrogen. What's the number? 5 carbons. What's the number here? 12 hydrogens. And we write it as the subscript. So this is the molecular formula. By the way, you have to define molecular formula like I have. You have to define displayed formula like I have. Please. Next. Now, what actually happened was scientists were really curious about certain things. Scientists said, wait a moment. If I were to make an alkene, if I were to write the molecular formula of an alkene with, let's suppose, 50 carbons, this is going to be very difficult for us. If the examiner said to write down the formula of an alkene with 50 carbons, a dumbo jumbo, what he would do is, he would say, okay, sir taught us to write the molecular formula by counting the carbons and hydrogens. Now you have in 50 carbon alkene, you're going to have 50 carbons. How many hydrogens do you have? Let me draw it. So a dumbo jumbo student will start to draw or start to write all the 50 carbons and then finish off the bonds with hydrogens and then count the carbons which are 50, count the hydrogens which will be a number, and then he's going to write it. That's going to take the entire exam time, and scientists were really fed up of doing it like this. And what they noticed was a simple guy like me got up and he said, okay, there's an easier way to do this. Instead of figuring out the molecular formula by first drawing it and counting it, you can easily do it by coming up with something known as a general formula. You can come up with a general formula for every single family. And if you look at the alkane family, you'll notice a trend. And that trend will be followed by every single alkane. This trend that you're going to see in the formula, it'll be followed by every alkane. It'll fall under the umbrella of an alkene if the trend is followed. The question is, which trend? Let's check the trend out. See, in all of these cases, you'll notice something. The number of carbons that you have, hydrogens are twice the number of that plus 2. You'll see this. If carbons are 3, hydrogens are twice that number plus 2. If carbons are 4, hydrogens are twice that number plus 2. See, 4 times 2 is 8 plus 2, 10. We've even counted this stuff out. If carbons are 2, hydrogens are twice the number of that plus 2. If carbons are 5, hydrogens are twice the number of 5 plus 2. And they came up with a generic way. Of writing these formulas. They said, hey, in order for something to be an alkene, whatever number of carbons you have, hydrogens will be twice the number of that plus 2. And so they said, if the number of carbon is n, if they said that if the number of carbon is n for an alkene, let's suppose in this case it's 5, hydrogen is twice that number plus 2. So if the number is n, hydrogen will be twice that number, which is 2 multiplied by n is 2n plus 2. And so this is how they came up with the general formula for alkanes, which is CnH2n plus 2. So in order for any molecule to be an alkane, it must fit the general formula of CnH2n plus 2. So it is an alkane if it fits the general formula for it. If it fits the general formula for it. So what exactly is the general formula? A general formula is a particular formula. It's the molecular formula. The general formula is in fact the molecular formula, but in terms of n. They've generically written it, right? It's the molecular formula in terms of n, where n represents the number of carbons. Where n represents the number of carbons. And remember, this general formula will be different for every single family, and in a particular family all the molecules will follow this formula. All the molecules will follow this general formula. It will fit this general formula for that particular family. So if I say, if you were to write an alkene of 50 carbons, what should be the general formula? What should be the molecular formula for it? Instead of drawing it and counting it, I can use the general formula, which is what? If you have 50 carbons, how many hydrogens should you have? 50 times 2. Whatever carbons you have, times it by 2 plus 2, right? So 50 times 2 plus 2. And so what should be the molecular formula for an alkane for having 50 carbons? It should be C50. Hydrogens should be twice the number of that plus 2, which is 102. And why is this the formula for an alkane? Why is this particular fella an alkane? This is a very common question asked by the examiner. Why is this an alkane? The reason that it's an alkane because it fits the general formula of alkenes, which is CnH2n plus 2, and let me show it to you, examiner. C50 H2 times 50 plus 2, that equals to C50 H102. This used to be tested in O level IGCSE for 2 mark. In AS level it's going to be tested for 1 mark. Done? Now that's the idea of general formula. We derived the general formula by just looking at the trend, right? Now is C50 or no, is C45 and H90 an alkene, right? Is this an alkene? If yes, why? If no, why? And also give me, if you guys do not agree with it, tell me the correct version of it. If you do not agree with it, tell me the correct version of it. Shabash, do it right now. I'm here to fix the O-level basics. Shabash. Give me the why, don't tell me the answer, don't tell me no, yes, no, don't tell me the correct bit, just give me the explanation. Is this an alkene? The answer is, you all are right, no, this is not an alkene. Why is this not an alkene? Because this is the reason, this is the explanation. It does not fit the general formula. It does not fit the general formula of alkenes, which is CnH2n plus 2. And then what would be the correct version for it? The correct part would be, the correct alkene for it would be Cn, which is C45, H2 times n, twice the number of carbons, which is 90, plus 2. Right? I can even write it. You have to show it to the examiner. Examiner does not like it like this. He say twice the number of carbons, 2 times 45 plus 2. And so that gives me C45 H92. And that is basically the formula of an alkene. Done. That's the correct version. So you have to be able to explain it to the examiner. Why is C30 H62 an alkene? Why is this an alkene? Why is C30 H62 an alkene? Hanji, why? Because it fits the general formula of an alkene. Next, why is CH4 an alkene, or is CH4 an alkene? Now answer your own question, Chaudhry Ali Afnan. If you studied O levels from me, you must have known this answer. But now you answer your own question. Is this an alkene? If so, why? Yes, Afnan, this was your question at the start, which every student has in O levels and AS level. And I love this question because a lot of teachers just say it is an alkene because it's an alkene. No. Now answer your own question. No, Raima, pathetic answer. Pathetic answer. Sorry, but what do you mean? Because it has a single bond. Is this the reason why something is an alkene? Abhi tak hum chat se chalang maar the. What were we doing up until now? Yes, Fatima is absolutely right. It is absolutely an alkene. Yes, it's an alkene. Why? Because it fits the general formula of an alkene, which is what? CnH2n plus 2. C1, H twice the number of that, plus 2, and that is CH4. We don't write 1. And that is the reason, Chaudhry Ali Afnan, that this CH4, which is called methane, because one carbon alkene is meth, and the ANE drops down. That is the reason why methane is basically an alkene. Even though there is no carbon-carbon single bond, but if there were another carbon, it would make a single bond with it. So where do you classify methane as? Although you might not say it's saturated, we do say it's saturated. Even though you don't see carbon-carbon single bonds, we still call it saturated. We still call it saturated because there is no other carbon. If there were any other carbon, it would still make a single bond with it. And why is this an alkene? As far as this question is concerned, why is it an alkene? The answer is right in front of your eyes, because it fits the general formula of an alkene, which is CnH2n plus 2, and it does not fit any other general formula. That's why scientists had to categorize methane as an alkane. And by the way, it's the smallest and the simplest organic molecule to ever exist. Smallest. Chaudhry, ठीक है? Happy? Happy, Chaudhry? Please give me an affirmative answer or no. Yes, no, happy or not? Hello? Happy? Phone लगा के चले गए. चलो, I don't know. Maybe he's using Instagram or something. Done, guys? Now, that's the idea. The next part is known as empirical formula. The next part is known as empirical formula. Empirical formula is what, my dear fellas? Empirical formula is basically the simplest whole number ratio. It's the simplest whole number ratio of the atoms of each element in a compound. Now you guys might say, sir, what in the hell are you saying? We know what this is, man. If you have glucose C6H12O6, what's the empirical formula for it? The empirical formula is what? Is the simplest whole number ratio of the atoms of each element in a compound. So what you do is you take the ratio of all of these, 6 ratio 12 ratio 6. Can all of these be divided by a particular number? Can all of these be divided by a particular number? Yes, they're all divisible by 6. You can first divide it by 2 and then divide it by 3, but you have to keep on dividing it until all of them until and unless all of them can be divided by a single number. You should keep on dividing, because you have to reach the simplest whole number ratio. The moment any number cannot be divided, that's your answer, right? So 6 ratio 12 ratio 6 is actually 1 ratio 2 ratio 1. Now this can further not be simplified into whole numbers. You can divide it, but then I'll give you points. So this is the simplest whole number ratio, which is CH2O. This was the carbon bit, this is the hydrogen bit, this is the oxygen bit. So this is known as empirical formula, the simplest whole number ratio of the atoms of each element in a particular compound. And we've also done this in moles and stoichiometry. Similarly, if you have C2H6, what's the empirical formula for it? 2 ratio 6. Can this be further simplified? Yes, this can be divided by 2, 1 ratio 3. So the empirical formula is CH3. It's just a ratio, remember. It just tells me the ratio. It's not how the actual molecule looks like. It's just a ratio, right? It's just a ratio between them. And that's it. It's the simplest whole number ratio of the atoms of each element in a particular compound. Hamza is saying, what's the use of empirical formula? The reality is the molecular formula. What's the use of it? Hamza, you've already studied the use of it in moles and stoichiometry, which is the idea that it's actually the empirical formula which you end up with first. After you perform mass spectrometry, what happens is you get percentages of every single atom in that particular compound. And once you have the percentages, you use your moles and stoichiometry knowledge to actually figure out the simplest whole number, which is the empirical formula. And then you also have the molecular mass from it. So from the empirical formula, you go into, and the molecular mass, you actually figure out the actual molecular formula. That's the idea. So in reality, whenever you discover a new organic compound, you first of all calculate the empirical formula for it through mass spectrometry, which gives you percentages of, or different analytical techniques, which gives you percentages of every single element of in that particular compound. And then from that and the molecular mass, you actually figure out molecular formula. And we've done abundant questions in moles and stoichiometry. Done and dusted. Yes. Easy. So that's the idea of empirical formula. What's the empirical formula of CH4? Methane. What's the empirical formula of methane? Hanji. What's the empirical formula of methane? The empirical formula of methane is again CH4. Because it's 1 ratio 4, you can't further simplify this. Can you? You can't further simplify it. An MCQ once came, can the empirical formula and molecular formula are always different? No, not necessarily. They can also be same in case of methane. As long as it's the simplest whole number, the molecular formula can also be the simplest whole number ratio. So remember, empirical formula can be equal to the molecular formula. There's no big deal about this, right? Yeah, that's the idea. C3H8. The empirical formula is the same as the molecular formula. There's no big deal about it. Like it is what it is. You can't further simplify 3 and 8 into a whole number, can you? You can't. Done? 2 minutes break, and then we're going to learn the last formula, which is called skeletal formula. And this is new for AS level students. Right? And we're going to do the same for every single family, by the way. And we're going to learn isomerism in the first bit of organic chemistry. So the first bit of organic chemistry is to quickly run you over your basics and quickly teach you naming and isomerism and all of that good stuff to make you as strong as possible, because you will not be able to understand a teeny bit of organic chemistry until and unless you are very solid with your names and with your diagrams and drawings and all of that stuff, because it's like a puzzle. So that's my way of teaching organic chem, and you'll see you'll be masters by the end of this organic chem course. You guys will be masters of organic chemistry, and this is my promise to each and every one of you, provided you take my classes and do not just ask questions and then leave the class, or maybe watch Instagram reels or something like that, right? That's on you guys. So I'm going to take a 5-minute break. My shoulder started to hurt once more. Do pray for me. I am highly vitamin D deficient, and I know prayers have a lot of benefits to it. So they do really work. I'm going to start my medication. I'm highly deficient in vitamin D because of my office work. I sit all day in my home, and that's the biggest problem that I have. Not in my home, but either in my office or in my workspace, and I use my laptop, so my bones have gotten weaker, and yeah, that's not good. I need to go out and exercise more, but I think even for now I just need to spend more time with you all, and then later on I'll work on my health. But obviously we all know health comes first, whatever, but there are far greater things for me. I have to create leaders of the future. So I'll be fine. So I'm just gonna take a 2-minute break, guys. A 2-minute break, and do keep me in your prayers, right? 2-minute break. My shoulder is burning, and it's a hell of a burning sensation. It's like a pain in my bum because of this. So yeah, just give me a moment. Yeah. Okay, guys. Continuing with skeletal formula. It's also sometimes known as the line angle formula. The line angle formula. Now, what exactly is a skeletal formula or the line angle formula? I also call it the zigzag arrangement. This is my word for it, the zigzag arrangement. I don't know if a book calls it this or not, but this is what I've come up with, the name for it, the zigzag structural arrangement, right? Or the line angle formula, or the skeletal formula. What exactly is this? It's this. Zigzag, 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 zigzag. That's called skeletal formula. Sir, are you joking with us? Is this a skeletal formula? What exactly have you drawn? Are you just kidding with us? No, I'm not. This exactly is what a skeletal formula is all about. Sir, what does this mean? You've drawn some mountains for us like back in the day when we used to draw them when we were in prep or grade 1. No. This is not that. These are basically nodes. This is a node, this is a node, this is a node. These are all nodes. Node. And each node actually represents, fun fact, drum load, each node represents a carbon atom. That's what it is. So if I ask you, in this particular structure, how many carbon atoms do we have? So you just count the number of nodes. 1, 2, 3, 4, 5, 6, 7. You have 7 carbon atoms. That's what a skeletal formula is. You show carbon atoms through these nodes. Right? And the next bit you need to know is, sir, where have the hydrogens disappeared? Where have the hydrogens disappeared? I can't see hydrogens. Sir, I can't see them. You won't be seeing them anytime soon, because in skeletal formula or the line angle formula, we do not show any hydrogen atoms. We don't show them. It's assumed that they are all present. It's assumed that all the other hydrogens are present. So if this is a carbon atom and it has made a single bond with another carbon atom, these are the hydrogens which are present. It's also bonded to 3 hydrogens. Similarly, this carbon is bonded to left and right. It's bonded to 2 carbons. Carbon can make a total of 4 bonds. These are the hydrogens which are present. These are the hydrogens which are present. We don't show hydrogens. They are present. I can show it to you right now with these dotted lines. These are the hydrogens which are present all the way, but we don't really show them in skeletal formula. And the question is, why do we need skeletal formula? These are hydrogen atoms. Whenever you don't have anything else shown, it means that there are all the other bonds that carbon has made is with hydrogen atoms. So hydrogen atom, hydrogen. So the first advantage of this particular formula is, the first advantage of using skeletal formula is that you basically can draw large structures very efficiently. You can draw these large structures very efficiently. Yes, a single line represents a single bond. Yes, they are all bonds. And each node represents a carbon atom. Absolutely, you're right? Now, the first idea is that it efficiently makes you draw these structures. But the major idea behind the skeletal formula was not to just quickly draw structures. Now, this was not the idea behind it. The idea behind it was that it shows bond angles clearly, more clearly compared to displayed formulas. Because understand that in displayed formulas, when you guys looked at displayed formulas, it gave you guys no idea whatsoever about the bond angles. Look at this displayed formula, methane. It is not telling me the structure of this methane. It is not showing me what the actual shape, not the structure, but what the actual shape of this methane molecule looks like. What are the actual angles? It doesn't show me anything of this sort. It doesn't show me, because I know that methane, it's a carbon bonded to 4 hydrogen. If I want to draw the shape for it, chapter number 2, chemical bonding, it's something like this. It's a tetrahedral shape with bond angles of 109.5. And fun fact, let's check the skeletal formula out. This skeletal formula gives you the right representation. It is showing me that every single carbon is tetrahedrally bonded to these other atoms, right? It's a tetrahedral shape, across every single carbon. See, if you use your eyesight a little and your imagination a little, it's showing you those tetrahedral bonds. So it's basically giving me a more clearer idea about the bonds and the angles. That's why it's also called the line angle formula, because it gives you a clearer idea about the angles. Each line represents a bond. So what we actually do is, if I were to draw this straight line, each node represents a carbon atom. These are both carbon atoms, carbon and carbon. So you have 2 carbon atoms, and if I have not drawn anything else, that means all the other bonds are with hydrogens. We don't draw them, but if you want to visualize them, this is how they are added, right? So you have 2 carbon atoms, and we do not show hydrogens, right? We do not show hydrogen. We represent carbons by the ends, with the ends, or with the junctions. So at every junction there's a carbon, and at both ends there are also carbons. So at ends you have carbons, these are also nodes, and every junction is also a node which represents carbon atoms, right? Every junction of the line, right? So we don't show hydrogens, but remember, we always assume that they are present. But there's also another idea. If there are other atoms present, which we'll see later on, you have to show those other atoms. The only atoms which we don't show are hydrogens, because they are very common. They are present in almost all organic molecules. They're very common. That's why. Right? That's one of the reasons. So other atoms need to be shown, like oxygen, nitrogen, sulfur, all the other atoms, and even the double bonds and the triple bonds need to be shown. So it's only the double bonds and the triple bonds also need to be shown. It's only the hydrogens which we say that we don't need to show them, because they are abundantly almost in every organic molecule. And if there are no other bonds, that means that all the other bonds are with hydrogens. All the remaining bonds are with hydrogens, right? It is also used to show the double bonds and triple bonds. How can you show double bonds and triple bonds? Just like this. If you were to have a double bond right here, you draw one line on top of this line. Now this is a carbon atom, this is a carbon atom, and it's basically carbon double bonded to carbon. That's it. Carbon double bonded to carbon, right? So you show a line on top of this. This does not mean that you have 2 carbons here and 2 carbons here. No, it's the same 2 carbons, you just draw a line on top. And if you want to show a triple bond, you show a line on top and a line at the bottom. That's a carbon-carbon triple bond. This node represents carbon, carbon, and this basically means that carbon is bonded to the other carbon, but there is a triple bond between the two. Right? Now the question is, sir, let's draw the skeletal formula for the first 10 alkanes. Let's draw the skeletal formula for the first 10 alkanes. Remember, in skeletal formula, we do not show hydrogens. And since alkanes are saturated hydrocarbons, that means what? That it must be carbon-carbon single bonds. So we have to represent them, these nodes and the ends of each junction of the nodes of at each junction, and the start and ends of these lines are also carbons, right? And hydrocarbon means carbon and hydrogen atoms only. Carbon and hydrogen atoms only, right? Carbon and hydrogen atoms only. So now, since carbon will already be fixed due to the name, hydrogens will not be drawn. It'll be assumed that they're already present, right? Let's start off with the first 10 alkanes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to go reverse in the reverse order, right? So let's start with 10. And the trick to this, I'll give you guys a tip. Count in pair. Whenever you start to draw the first round, count it as a pair. Count it as a pair. The first line should always be counted as 2. Like if I were to draw 10 carbon alkane, I'll draw first line, these are 2. See, 1, 2. So I'm going to say 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it, right? So count it out. Now count it out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So whenever you draw the first line should be always counted as 2, like this: 2, 4, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it. Then the alkene with 9 carbons, again, look at how I do it. Look at this: 2, 3, 4, 5, 6, 7, 8, 9. There's nothing new about it. That's easy, and you could still verify it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Similarly, 8, 2, 3, 4, 5, 6, 7, 8. That's it. Next, 7, 2, 3, 4, 5, 6, 7. So always count the first line as 2. See, because it is one node and another node, right? Again, 6. A lot of students make this mistake, by the way. Again, 6, 2, 3, 4, 5, 6. 5, 2, 3, 4, 5. 4, 2, 3, 4. 3, 2, 3. 2, right here. And 1 is just a dot. But you'll never be asked to draw the skeletal formula for one carbon. Never, ever, ever. No, you'll never be asked. But this is the skeletal formula of the first 10 alkenes. How easy is this? And by the way, each node represents a carbon. Each node is representing a carbon. And all the other bonds that you have are with hydrogen. But obviously, we aren't showing this hydrogen, 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 hydrogen. This carbon will be bonded to 3 hydrogens right here. And this is also bonded to 3 hydrogens right here. But we don't really show the hydrogens. Isko ulta nahi add kar sakte. It's up to you. You can also start like this: 2, 3, 4. It's up to you. Normally the convention is you start with a hump and then go at the trough. It's normally like this, but if you want to start like this, it's up to you. You know, it doesn't really make a difference, by the way. The convention normally is that almost all the books start off with this. But this is equally correct. You can start off like this: 2, 3, 4, 5. It doesn't really matter. मतलब टर्नीली मारनी थी तो कुछ नहीं होता, मारने टर्नीली. Let's piss off conventional followers. Then you might find a conventional examiner who will flip you off then. That's it. So what exactly is the skeletal formula? Now let's look at the definition for it. The skeletal formula or the line angle formula, we've looked at the advantage for it more efficiently, and it shows the bond angles more clearly, and you've seen it. It shows me the tetrahedral shape more clearly, but that is in fact clear. You'll never be asked to tell or write the definition of a skeletal formula, but if you were to write it, you just say it's also known as the line angle formula. It represents, each carbon is represented by a node, and it shows the bond angles more clearly. Hydrogens are assumed to be there, but they are not drawn, and you have to separately show oxygens, hydrogens, nitrogen, all the other atoms. You have to show them in the skeletal formula. If, for example, there's a carbon double bonded to an oxygen, and it's like, you have 3 carbons, 1, 2, 3, and this middle carbon is double bonded to oxygen, you have to show this double bond with oxygen like so. And you learn more and more later on as we properly learn names and families, right? The last formula is called the structural formula. And because I'm getting a little tired, guys, do you want me to teach you structural formula? Let's learn structural formula. Tomorrow we'll learn structural formula. It's like a 5-minute concept, but my shoulder is killing me. So I'm going to club it in tomorrow's class, right? I'll upload this. In tomorrow's class, we'll learn structural formula and we'll learn advanced naming. And I will also be changing the link for the AS level, because obviously this is now registered students only. So if you want to register, you can contact Miss Naiba. Abhi to party shuru hai. You'll see how I teach you organic chemistry. This was all a recap. You'll enjoy it, I promise. I'll teach you guys a certain concept, inshallah, in which you will be able to decipher all the mechanisms on your own. Instead of rote learning them, you'll be able to decipher them, because organic chemistry has 4 to 5 ideas behind it. If you properly understand what a nucleophile is, an electrophile is, and how do you actually map it out like a Lego, it'll always it'll always work out for you. Sir, what's the skeletal definition? There's no definition for it. The examiner will never ask you. You just say it's a line angle formula in which you show carbons at each node. I literally just said it as each node and blah blah blah. You don't show hydrogens, and you show other atoms bonded. That's it. That is the definition. Yeah. But you don't have to learn the definition for skeletal formula. That's not a part of your course. You just need to know how to use it, right? But that is what it is. Why do we use skeletal formula? What's the purpose? Rayan, I've already talked about it. Sir, would it be possible for you to have an extra class whenever possible to finish the syllabus by Feb? Fatma, please. Please don't ask such questions, kiddo. I don't know. My time is till 31st March. This is my time that has been promised with you guys, and very early on. So it's 7 to 8 month course. But it's my job to see when I want to finish it, because now we're already done with a lot of things, right? It's very easy for me to finish it, but I want to make sure that I do a lot of practice. Okay. So I don't want to bore you guys with organic chem. In between organic chem, we'll keep on practicing topic wise questions like we always do for all the other chapters. Okay. And I'll change the link for this. Sir, there are unregistered students in this class. Please change the link. मतलब जालिम लोग हो. Khair, you guys are also right. Why should you not get the stuff for it? Okay, chalo, done. Sir, if we want to register, how can we register? Contact Miss Naiva. Miss Naiva is actually even calling me right now. But contact Miss Naiva. I'll write Miss Naiva's number down. Miss Naiva's number is +92 318 177 2015. This is Miss Naiva. She's the coordinator at Conceptuals. And yeah, that's it. Chalo. Done, guys. Bye. Ciao.